So this is not just segmentation for tumor, but also taking it further for patient survival prediction and things like that. So let me thank the session chairs first, and also the conference organizers who invited us here to this conference. This work, like all other previous works, is not just done by myself. I'll acknowledge my collaborators and all the students and postdocs, at least some of them, in the end. And this work has been supported by multiple different grants. So following Peter's clue, of course I had it before, but let me do this just to show you where I'm from, right? So there is this map of US, and that's the state of Virginia, this one here. And Washington, D.C. is right there, because some of you may know Washington, D.C. We're right there on the shores of Atlantic, right? So that's where the city of Norfolk is, and that's where this university is, Old Dominion. So this data is a little bit dated, perhaps 3-4 years old, but at least gives you some idea. We have about 25,000 students. There's this split of undergraduate and graduate, about 5,000 graduate, rest of undergraduate. It's now about 88 million research expenditure. It's about 100 million now. We do not have any medical school. Usually the medical school brings a lot of money. So that's why this data goes up for the schools that are medical schools. However, we do have medical school close by that we work with. Again, another 1 or 2 slides about my lab. Currently, there are about 9 PhD students, a couple of undergraduate students. There are actually 2 postdocs now, and we have funding from multiple different agencies. About the areas of focus for this lab, these are some of the examples. We work in biomedical signal image analysis, autism, then of course machine learning, deep learning, human machine-centric recognition. We also work in environmental geoscience applications and autonomous robotics and intelligent systems. So everything to do with computer vision, machine learning, things like that. So now back to this talk. So here's a brief outline of this talk. And again, thanks to Peter, and I think the previous speaker, they already asked about the background of the audience, and mostly these are your students, both undergraduate and graduate students. So I'll try to orient my talk a little bit to serve your interest. So there are 3 parts, but I do not have time really to go over all the 3 parts. So primarily I'll talk about the first part, and I'll show you some results for the second 2 parts. So first part is about abnormal brain tissue segmentation, and I'll tell you why this is important. And this includes tumor and lesion segmentation. So these are sort of, for example, stroke patients, they get these kind of lesions in the brain. And then we take that, and so this first part is primarily for machine learning type methods. The second is about taking that to deep learning, which you have seen in some of the previous talks. And then we take that, the results of these to identify the patient's survivability probability. So this chart is strictly for US. However, worldwide, this will be a lot larger in terms of prevalence for brain tumor, right? So in the US, every year, this chart basically shows you the new cases and the deaths. So if you go as far back as 1990s, and so for the last 20 or so years, actually 30 or so years, this figure pretty much stayed steady, right? So no matter what we do, how much money we pour into this, the number of deaths still remains pretty much same, right? So that tells us that there is room. And at least, like I said, the trend is similar worldwide, even though that data is just for US. Okay? Now, just because I said this method is also applicable to other types of lesions, so I don't know, I think there was some timing set up for this. So this is also, again, data for the US for stroke patients. So about 800,000 or so people have strokes, right? It's fifth leading cause in the US. So anyway, again, this data is also representative of the trend in the world. Now, going back to the brain tumor, of course, there are different types of brain tumors, right? You may know, in fact, if you look up the WHO, the guideline, you'll see that the types of tumors, brain tumors, for a standard textbook, it could be like a couple of pages, right? Just looking at the different types. Essentially, the ones that you're looking at here is the CNS, the central nervous system tumor. So in this case, about 30% of these are brain and CNS tumors. Within that, we're looking at this GBM, the glioblastoma multiforme, which is the most lethal type of brain tumor, right? And in fact, I might have in the next slide or so, the prognosis for this type of tumor is really bad. It's somewhere between a year to year and a half, right? So for this GBM, the glioblastoma multiforme tumor that you're looking at here, there are, of course, different grades. So the prognosis that I told you is the highest grade, grade 4, right? Of course, if the patient is lucky, and if these tumors are detected earlier, like in stage 1, 2, or 3, or primarily in 1 or 2, then it could be a good news for the patient, as you know. So the goal of this work, what we're trying to do here, is trying to really supplement or complement what the radiologists do. We're not, like previous speaker mentioned, we're not trying to replace anything. We're trying to help them. How? So for example, if someone goes to a clinic, right, with headache or some problem, so the first thing that they'll do is they'll take these MRI scans. And depending on the size of these clinics can have perhaps 30, 40, 50 patients per day, right? And for each patient, the volumes of images that are generated is huge. And if you have any experience, what happens then is these volumes, and these are multiple modalities, by the way, depending on the MRI scanner, the orientation and the strength and all those things, they will generate multiple different volumes, different types of volumes. And I'll show you at least a few of them later on. So depending on how many volumes are generated, again, per patient, this could be hundreds of images, all right? And then what happens is the radiologist then goes to this dark room, right? It used to be just those sort of printed slides in the past. Now these are all digital. But nevertheless, they go to this dark room and they spend whole day reading these slides. So it's tedious, it's difficult, it's error prone, and in fact, if you give the same volume to 2 to 3 different radiologists, right, except for some obvious lesions, tissues, abnormal tissues, you will have differences. And that's known, that's common. If you just ask radiologists, they'll tell you that, right? In fact, more critical, in fact, I'm actually going over some of the slides that I have later on, but let me just go ahead and talk about it. Then I can skip those slides. So depending on how difficult the tumor is, it's essential for the radiologist to draw a boundary around the tumor. Why? Because using that boundary, then they can compute the volume of the tumor. And it is necessary to compute the volume because then the physicist, radiophysicist, then calculate the dose, for example. Or the surgeon can figure out how much tissue to take out if there needs to be a surgery, right? So for all these reasons, it's very critical to understand the boundary of the tumor. And for many different types of tumors, especially those GBMs and other tumors, many times the boundary is not well defined. It's blurred, okay? And when you say tumor, in our common language, we just think it's just one homogeneous type of tissue, tumor. But in practice, it's not, right? So there is the problem. So if you want a machine, so now what I just told you is the problem with human being, the radiologists who are trained, right? And even then, they are having problems, like I said. So for this reason, oftentimes what happens is whenever you want to do something automated in this domain, the way that you get the ground truth, because you need to have the reference to compare, right, how good or bad you're doing. So what happens is you actually bring multiple different radiologists together, and then you have the consensus ground truth. Okay, so that is then taken as the ground truth to compare. So now, going back to what I was telling you, so if the human doctors, the radiologists are having this problem, think about a machine trying to do the same thing, right? It's not a trivial problem, right? So I basically went over all those stuff, so I'm going to skip. So this is one thing that I need to tell you though. Prior to 2016, most of this grading of the tumor that I told you, 1, 2, 3, stage 4, this was done mostly based on the histopathology, right? So what is histopathology? Basically, the radiologist or pathologist goes into the brain and takes out the tissue and looks at under the electron microscope and looks at the morphology, the type and shape and all those things of the tissue, and based on that decide what grade it is, right? So that was the practice in most cases. But after 2016, actually the genomics is also added for the grading. Okay, so in other words, for us, for the computer scientists, for those who are basically ignorant of this stuff, we need to work with not only just the radiologist or pathologist, we also have to work with the geneticists if we can, right? To be able to bring together all this information into the grading, the classification, if you're looking into this. This talk, though, by the way, we are working in this area as well, but this specific talk today does not go into the genomics part. This is only based on the radiology, on the radiomics part. So what I was trying to tell you about the tumor, when I say tumor, it's not just a single homogeneous tissue, right? So essentially, look at these two slices. This is the so-called tumor boundary, right? Within the tumor, you see different intensity of tissues, right? They actually represent different types of tissues here within the tumor. And these are all different types of abnormal tissues, right? So for example, there will be the black area is inside, darker area. So this darker area could be perhaps the necrosis, the cell that is dying off. As the tumor pushes out, grows out, the center cells, they start to die off, okay? And as they are pushing out, now so this is MRI, right? So usually how this is done is usually the dye is injected before the MRI is done. So that those dyes, the dye is absorbed by these abnormal tissues, and then they light up in the MRI, right? So depending on different types of abnormal tissues, you see different intensities, okay? So some of them will be enhancing tissues, meaning they actually light up really good. Some of them could be non-enhancing tissues, but still tumor. Some of them could be surrounding areas that are edemas, meaning tissues swelling up as the tumor is pushing out, right? And all of these are important. For example, edema is important to understand the survivability probability of the patient. Okay? So all of these abnormal tissues are important to understand, and not only just understand, but to begin with, to be able to segment each of them specifically for different reasons like I mentioned before. All right, so I talked about most of these things, so let me skip. Okay, this is another thing that we need to understand from the automation perspective. If you look at these MRI slices, you will see all these different, these are just some of the examples of problems, depending again on the imaging modality and how the images are captured, right? So this shows some of those different artifacts that you might see in an image, right? In addition to that, for most of these things, there are multiple different major manufacturers of these imaging magnets, right? Philips, Siemens, GE, and inherently there will be differences between these different scanners, okay? So you'll have to be able to account for the differences because you do not know these images are coming from what imaging scanner, okay? So having said all those, talked about all those issues, here's what we set out to do. We basically tried to see if we could come up with some method to be able to segment these different tissues, abnormal tissues within the tumor, right, as closely as possible. So this shows the machine learning pipeline somewhat similar to one of what Peter showed for his case. So this is similar kind of thing. So what we have here is those stacks, the volumes, right? We need to do some pre-processing to be able to address those artifacts that I showed you earlier, right? I'm not going to go through the details because it's going to take a long, long time. I'm just going to show you the overall. And then we extract some features. One of the things that we noticed early on for these tumors is if you take out the tumor tissues, you'll see that these are jagged surfaces. Okay? These are very rough surfaces in most cases. Of course, they get different types of tumors, will have different manifestations, morphology. So for these ones, the ones that we're looking at, will have the jagged surfaces. So we looked at the surface characteristics of these tumors, and then we saw there's a possibility that we could perhaps look at the texture characteristics of these tumor tissues, right? Because the texture will capture those jaggedness in the surface. Not only that, we would like to see it at different resolutions, right? So mathematically, I'm not going to go through the slides, I have the slides here, but I'll just tell you the concept of it. So essentially what we did, I'm talking about this part here for the feature, what kind of features that we're looking at, and what is new about this. So we looked at these images, we tried to see if we could capture the roughness of the surface and also at different resolutions. So mathematically we combined those two, the fractalness, which captures the texture, and the multi-resolutionness, meaning at different scales, and we combined this into fractal Brownian motion kind of, again, this is a very loaded term, I'm not going to go through the details, but essentially that's what it does. It combines the texture characteristics at different resolutions, all right? So that's what we did. We came up with these different features in addition to just regular intensity, of course. And then this is your typical classifier, right? Random forest in this case. So random forest basically we trained and then with, of course, some different folds for validation, and then came up with the segmentations of different types of tissues, all right? And then we can take those segments, do the 3D volume, and take it for something else, and compute all those sensitivity, specificity, accuracy. And in this case, we also want to see how good the segmentation, one of the metrics is called DICE, of course there are many, which basically computes the overlap. So remember I told you that for these kind of things, there is no consensus. So essentially you bring together multiple radiologists and have them give you the ground truth, right, consensus. So you take that, and then we take our method here, put them together and see how good they overlap on each other. And this dice does that. So these are some pre-processing. You have to basically, there is this skull around it. We're just looking at the soft tissue, so we don't need that hard tissue around it. It's just a distraction. So we take the skull out. We do some resampling and aligning co-registration. So co-registration is also important because what happens is how many of you have seen an MRI scanner? Those are big magnets, right? So when the patient is put inside, of course, they try not to move, right? But still, it's difficult to stay steady, right? Stable, especially if these are kids, because some of these studies are done with the kids. So what happens then, because of the movement, the brain moves, right? Essentially, the stuff inside the head also moves. So we need to be able to register them to some template so that we do not shift the stuff inside the brain, in this case the tumor. Right? So that's why the code registration is important. And I talked about the bias field correction, homogeneity corrections. Those are the standard corrections that we need to make to take care of those artifacts. So these are the few slides that I have on this texture mathematical modeling for the feature that I mentioned just briefly before. I'm not really going to go through the details because there are multiple publications, and I'll show you some more in the end. You can look them up, or you can, if you want to know more, you can send me an email. I can forward you some of those papers. So let me not get to this at all because it's going to be challenging to explain all this here. So let me skip all those. But trust me, what this does, all of this, is there are two methods that we developed here. I can tell you that much. One is in frequency domain, another is in time domain, right? So essentially, all of you are familiar with Fourier transform, I hope, right? At least it does from time to frequency, right? So it's similar. So essentially, we looked at the spectrum in the frequency domain, and also we looked at the time domain, and we tried to compare to see which one gives us better result between those two. So this integrated framework that I was talking about before, that combines the texture with the multi-resolution, and you can actually develop the methods both in frequency and time domain. It turned out for us, the frequency domain was a better method. So I'm going to skip all those. So let me just get to the results. So essentially what happened here is, so these are different sequences. Like I told you before, depending on the strength of the magnet, orientation of the magnet, and things like that, it will generate different sequences, like T1, T2, flare, T1Cs with contrast agent. And also it turns out that different sequences are good for picking up different types of matters in the brain. Some is good for water content, some is good for white matter, gray matter, right? Different types of things. However, when a radiologist looks at this, they actually look at all the sequences. And in fact, at least these sequences that you see here. Okay? So it's not a trivial process, because that's the training that they go through. They spend like 5 years in the medical school, and then beyond that they have other trainings, right? So at the end of that, they bring together all those experiences, look at all the slices, different modalities, they bring them together to find the tumor contours, not just tumor contours, all the abnormal tissue contours within that, and then that's the end result of it. So for us to be able to replicate this, what we had to do, at that time I was in Memphis, you mentioned that I was in Memphis, so I was working with this St. Jude's Hospital. So I used to actually go, they have, and I'm sure every place has that too, all major hospitals should have that. They have these tumor boards, right? So essentially the doctors, once a week perhaps, maybe multiple times a week, depends on the volume, they get together, they discuss the hard cases, right? So I used to take my students and attend those tumor boards. They are like early morning, usually at 7 o'clock. So that's how we try to understand, at least as much as we could, how do they really do this thing. It's not trivial. And that's how you have to do. If you are, especially those of you, or all of you here are not in medical schools, right? So if you have anything to do, or you have to do anything with medical domain research, you have to understand the problem. And you have to go where the problem is. They're not going to come to you. So that's how you have to do, right? So you need to understand as much as you can. So here is the case. There are two sequences that shows this is segmentation using this method, and this is the ground truth, the way that I said before, right? And this is basically getting the 3D volume. So what you do here is you actually, I don't know if the movie is going to play or not. I'll try. It's not. I don't think it's going to play. So you could actually do the whole volume segmentation, which you do, or you could just do one slice at a time and put them together, right? You could do either way. But essentially, in the end, it should give you the complete volume, which is what you're looking for. And of course, if you slice it through, you'll be able to see the different types of multiple abnormal tissues within that volume. So we have been doing this for some time, but we started going to these challenges. This was back in 2013. You might know about this society in ICAI. That's a premier society in computer-aided detection and things like that. So they organize these challenges. It's every year now with the National Cancer Society. National Institute of Cancer, NCI, in US. So in 2013, our team was ranked third, and basically the method that I showed you there, using that method. And the next, so in 2015, or the next year, the 15th, we went to a different challenge, which was for the stroke lesion. And there are certain similarities between these two, brain tumor and stroke, right? So we were able to basically modify our method and participate in this challenge. And in this case, our rank was fourth for that case, for that challenge. Now let's move to the next two topics just quickly. So what we just showed you there is just a conventional machine learning method, right? Which is you extract features. Features are representative of what you're looking for. And then you basically run some standard classifiers, in this case random forest. And in fact, prior to that, we used SVA and others. Now, with the deep learning method, you don't have to go through this speech extraction process, right? That's the good part of it. The bad part of it is you need to have hundreds and thousands and millions of images, right? Which we do have in this case. Because like I said, a typical volume will have maybe 100 plus images, right? And they have multiple volumes per person. So this is a lot of images we're talking about. So that was a good application for deep learning. So in this case, then we took that method and then moved to deep learning. And it turns out that just pure deep learning may not be enough for everything, okay? Now, it may be risky to say that because deep learning has taken over the world. But if you can guide your learning, right? If you can guide your learning, that may have a better result. And that's what we have gotten here. So what we did is we had this just generic machine learning method, and then we brought in the deep learning, and then we fused that. And that is basically guiding the deep learning with the regular machine learning method. So again, the deep learning, I'm not going to go through the details. Essentially, this is the regular standard CNN. More recently, we're using UNet. You might have heard about it. And especially in biomedical area, bioimaging area, the unit is really way to go, right? But in this case, we're just using regular CNN. So here it is, essentially just showing you the block diagram of it. Like I said, there is no need for this case to extract the features, just get all those images, extract the relevant patches in this case. The patch also we had to do it to increase the number of samples, right? So we get those patches and then essentially train the CNN. And this block diagram shows those two methods. This is the CNN, the deep learning, this is the original machine learning, bringing them together. The level fusion, of course, if you are familiar with fusion, you can do fusion at many different stages, but different levels, right? So in this case, we do the level fusion, which is meaning in both cases, we already have the segmentation done, right? We already know this is edema, this is necrosis, this is enhancing tumor, non-enhancing tumor in both cases. And then we bring those levels and we fuse those levels, right? So it's a higher level fusion, right? You could do feature level fusion and other fusions too. So that's what we do here, and then finally you get those segments. So this is an example. Again, those are two modalities, T2 and T1C. This is the machine learning method, the RF segmentation. Of course, there are lots of false positives that you see here. This is the mask out of this, of course, after we clear out all those false positives. And then this is the fused outcome with, this is the binary mask out of the CNN, and when you fuse those two, that's what we get here. So one thing that we noticed is for CNN, it's very good to give us the overall boundary, right? Whereas for the machine learning method, it's very good to give us the details, which is expected because all those features that we have extracted, right, those were representative of different details that we see within the tumor boundary. So when we fuse those two, that's when we get the boundary and the details. So that's what I meant, the guided learning. And in fact, more recently we are doing end-to-end learning, which is a whole different topic. How we can have both this to influence the learning of this and then do completely from input to output learning and training. So this shows just a quick comparison for the performance. This is the regular machine learning case. The DICE, I told you, the overlap. ET is the enhancing tumor, and WT is whole tumor, meaning all the tissues together. And TC is the TC. I'm trying to remember. Tumor core, just the core of the tumor. Okay? So this shows the overlap between the ground truth segmentation and the machine learning method, the CNN, and this is the fused method. Now, just briefly, I'll talk about that maybe 2-3 slides, and then I'll summarize. So what can you do with these segments? I told you that segments are necessary for radiophysicists to find the dose, calculate the dose. It's necessary for the radiosurgeon to understand for surgery what to take and not to take out from the brain, right? It turns out that these volumes are also important. The tumor volumes are also important to understand how long this patient might survive. Okay? Of course, you need other information along with it. The age, the patient age, the history of the patient, and all those things, right? So we take those volumes. I'm not going to go through these discussions, but essentially, this is again showing you those different types of tissues. Each of them have certain implications for the survivability case. So we have, in this case, about 163 GBM patients. The distribution is like this. There are 3 categories, low, medium, and high. 10 months to 15 months to beyond 15 months, right? And those are the sequences. And in addition to just the MRIs, we also have the age information of the patient. And the labels that are given to us, this is actually a competition that we participated, Brain Tumor Segmentation Challenge in 2017. So the organizers gave us the labels for these tissue types, and also gave us for the training case, the levels for how long the patient survived, right? So those are given for the training. So usually these challenges happen in 3 stages: training, validation, and testing. All right. So for training, they'll give you those levels so that you can train your methods, and then validation, they have their own levels, but they don't give it to you. You just upload your results, and then they give you the results back. And testing is completely unknown to you. So all of these are basically done centrally. So this is showing you the overall pipeline. I'm not going to go through the details again. So essentially, here is the segmentation that I mentioned before, using one of those methods or some of those methods. And on top of it, then you do another level of extraction of the features. And then we had to go through some other machine learning methods, in this case regression, and then identifying the most significant features. And I do another level of regression analysis on that, and then recursive feature selection. And finally, the regression gives us the prediction of the survivability, meaning in what range, low, medium, or high. And we need to do that both for the unknown case and known case. This basically goes over some of those details. Let me just skip those. So we did 10-fold cross validation, and the accuracy, this shows basically the accuracy. The final accuracy that you need to know is the validation accuracy, 66%. So for this case, like I mentioned, we went to this challenge in 2017 for the survivability prediction. These are all global challenges again, and we came out first for this one. So that's the ranking for that case. These are the other two teams. So this is just a summary of different challenges so far that we have participated. Like I mentioned before, I think I mentioned that 3rd place, 2nd place, and the 1st place, and the 4th place for the lesion segmentation. In fact, just recently, this I did not mention to you before. This is for the grading, classification of tumor, right? So I did not talk about that at all for this presentation here. But this one is based on also histopathology data, right? And that one we ranked 2nd. This just happened in China last year. So in summary, we just showed you a method, or actually a combination of 2 methods for segmentation of different abnormal tissues within the tumor, right? That will give you the shape, size, and location, and the volume, of course. And then these are the different types of features that we have extracted for the machine learning case. Where are we going from here? So, like I told you before, the WHO tumor grading has changed. They are now included with the genomics as well. So we have now done some work combining this with genomics for grading. We are also trying to make this publicly available. There is this tool, 3D slicer, you might know. In fact, in medical image analysis, there are multiple freely available tools. So if you're trying to do any work, you should heavily use those tools, okay? Because people have spent years and years to develop those tools. So there's no point you starting from scratch. So start with those. Of course, those are not going to give you the publications though. You need to understand. Those will give you the starting point, right? But you should start with those and then go beyond that, okay? So this is one of those tools, 3D slicer. So we're trying to develop a toolkit. Actually, part of our grant is that, to develop a toolkit to go with this 3D slicer. So that's one thing. And of course, we are looking at more difficult problems that is how we can take these tumor segmentation volumes and how we can then take it to oncology. What we have just talked about here is radiology, right? So for oncology, when the oncologists look at these volumes, and then let's say they decide to do chemo on these patients, correct? So now they have to track them to see how the tumor is behaving, growing or shrinking or whatever, right? One of the difficult challenges for them, for example, let's say the patient has gone through surgery, but now the tumor has reoccurred. So this recurrence problem. So is it really a recurring tumor or something else, a dead tissue, right? And based on that decision, lot will happen to this patient. But as you know, the chemo or any other regimen is very difficult on the patient's health, right? So if the patient has to undergo another bout of chemo or surgery, he or she may not even survive. So those decisions are very critical, right? So now we're going into the oncology domain to see how we can track these tumors over time, and not just tumor, but also recurrence problem, and how can we differentiate that with recurrence with necrosis meaning dead tissues. When the tumor tissue is, radiation is done, the tissue is dead, right? So in MRI, they look strikingly similar, the dead tissue and the recurring tissue. So those kind of difficult problems, we're looking into those now. These are some of the publications. Some of them are still, these are book chapters. Some of them are forthcoming, 2020, 19, and others. These are the people that I really need to thank. This is not the complete list, though. And we have been working in this domain for more than 15 years. So I cannot possibly list all of them that have helped and worked in this area with us. With that, I'm done.